Welcome to Lecture 18, in which we will discuss two topics from Chapter 5. One is gate decomposition, and the other is stabilization of operators. And so we will begin with gate decomposition. The idea here, well, first of all, this is explained in section 5.4.1 in your book, which is begins on page 84. And the idea is that if Q is a single qubit transformation then Q can be decomposed as follows. It can be written as Q equals K of delta times T of alpha times R of beta times T of gamma, where K of delta is equal to E to the I delta times the identity matrix. R of beta is equal to cosine beta, sine beta, minus sine beta, cosine beta, and T of alpha is equal to E to the I alpha 0, 0, E to the minus I alpha. The matrix K corresponds to a phase shift by the angle delta. R is a rotation. R of beta is a rotation by the angle beta, and T of alpha is called a phase rotation by alpha. And if you actually substitute in to this expression for Q, what you would find is when you multiply everything out, you would get the following: E to the I times delta plus alpha plus gamma cosine beta, E to the I delta plus alpha minus gamma sine beta, E to the delta minus alpha plus gamma, and a minus sign, so minus E to the I delta minus alpha plus gamma, delta minus alpha plus gamma, sine beta, and finally E to the I delta minus alpha minus gamma cosine beta. And any unitary transformation can be written in this way, and depending on which unitary transformation you have, you can compare the entries in the matrix to the entries in this matrix, and that will allow you to find delta, alpha, gamma, and beta. So that is the claim, and in fact the book proves that that's true in section 5.4.1. And then there is a follow-up exercise to understand that better. And so let's look at that exercise. This is exercise 5.4. And I'll just take a look at one of these. We want to show that x is equal to minus I times t of pi over 2 r of pi over 2 t of 0. Now notice what has happened here is that okay, remember this is our standard decomposition for Q. The first term is K of delta, and then T of alpha, R of beta, T of gamma. So in this case, if you don't want to multiply everything out, what you can do is just use the form we have right here if you can identify all of the angles. So let's see if we can do that. Well, clearly alpha is equal to pi over 2. If we compare this expression up here at the top for Q with this expression here, we see that alpha is equal to pi over 2, and beta is equal to pi over 2, and gamma is equal to 0, and the only thing that remains is to figure out what delta is. We have e to the I delta times the identity matrix is giving us minus I times, we could understand the identity matrix to be in here. So what value of delta will give us e to the I delta is equal to minus I? Well, delta equals minus pi over 2 would work. So we'll say delta equals minus pi over 2. Now again, I want to emphasize that you could go ahead and you could use the equations. You could use this equation for the t matrix and substitute in pi over 2 to get t of pi over 2 here. And likewise, you could use this equation for the R matrix and substitute pi over 2 in here and get that, and then t of 0. Well, t of 0 is easy. That's just going to be the identity matrix. So you could get all of these matrices and multiply them out and see whether or not you get x. But what I'm going to do instead is just substitute directly into this final result that the book has obtained and see if we get x. And of course, as I said, that just is essentially the same thing. So let's see if we will indeed get the desired answer. So if we substitute into this equation the values that we have for alpha, beta, gamma, and delta, we will get Q is equal to e to the I, and then delta is minus pi over 2, so we have minus pi over 2, and alpha is pi over 2, so that's 0, plus gamma is 0, so this is e to the I0 times the cosine of beta. Beta is pi over 2, and the cosine of pi over 2 is 0. Then the next term would be e to the I, okay, delta plus alpha. Delta plus alpha is 0, minus gamma, which is 0, so again, e to the I0. And then the sine of beta, well, the sine of pi over 2 is 1. Down here for this term, we will have minus, and now e to the I, delta minus alpha. Okay, delta is minus pi over 2, minus alpha. Alpha is pi over 2, so we have minus pi over 2, and minus pi over 2 is minus pi, plus gamma, which is 0. So we have e to the or minus e to the minus I pi. E to the I pi is negative 1, and so is e to the minus I pi. That's negative 1. And the negative of negative 1, of course, would be positive 1. And finally, for this last term, we have e to the I, and then delta minus alpha, again, will be minus pi, and then minus gamma, 0, so minus pi here. And then cosine of beta, cosine of pi over 2 is 0. So this would be the value for the matrix Q given by this equation. And we see that the first entry becomes 0. Since this e to the I0 here is 1, 1 times 1 is, we have 1. And then, as was already described, e to the minus I pi is negative 1, so we have negative 1 times negative, so that's positive 1. And then here we have 0. And so indeed, that is equal to x. So we conclude that this is a valid decomposition for x. And the other examples given in exercise 5.4 are very similar. So, and the idea here is that actually any arbitrary 1 qubit, or transformation of 1 qubit can be written in this form. Now, another exercise deals with the topic of stabilization. This is exercise 5.5. And as your book tells you, the condition, or what stabilization means, it says that C is stabilized by U, means U of C equals C. And so the book gives us several operators and asks us to find what vectors are stabilized by those operators. And you perhaps recognize that this is just an eigenvalue problem. In other words, we could think of this equation as being the same as U of C equals 1 times psi. And so if you write it like that, you recognize that this is just, that psi is simply an eigenvector associated with eigenvalue 1. So when we're given an operator and we want to know the states that are stabilized by that operator, that's the same question as what are the eigenvectors of this operator that are associated with eigenvalue 1. So let's look at an example. The first case says in the first case, u is equal to x. Now, as we have just reviewed, x is equal to 0, 1, 1, 0. And so now we could go to the trouble of finding all the eigenvalues of x and all the corresponding eigenvectors, but in this case we're really only interested in the eigenvectors associated with the eigenvalue of 1. So let's just use that information and make this easy. So we have x c is equal to c. And so this becomes very simple. We're just going to let c, we don't know the components right now, but we'll suppose that they are alpha and beta. Then that means x operating on the vector alpha beta gives us alpha beta. And so let's see what that tells us. Well, 0, when we substitute in for x, we have 0, 1, 1, 0. Alpha beta is equal to alpha beta. And so if we do the matrix multiplication on the left, this gives us beta alpha is equal to alpha beta. And so if we compare the components of these vectors from either the first component or the second component, we come to the same conclusion, that alpha must equal beta. Now remember also that since c is a state, we have that the magnitude squared of alpha plus the magnitude squared of beta is equal to 1. So if we suppose, the way we can come to a final answer for this is we can say, if we write alpha in polar form, we're thinking now of alpha as being a complex number, so we're going to write alpha in polar form, which means that we're going to write it in this form. It's the magnitude of alpha e to the I phase of alpha. And likewise, beta is the magnitude of beta times e to the I phase of beta. And so now the requirement that alpha is equal to beta, so let's say since alpha is equal to magnitude of alpha times e to the I phase of alpha, and beta is equal to magnitude of beta times e to the I phase of beta, and alpha equals beta, and magnitude of alpha squared plus magnitude of beta squared equals 1, then what can we say? Well, alpha equals beta implies that the magnitude of alpha e to the I phase of alpha is equal to magnitude of beta e to the I phase of beta. Now, at least one of these magnitudes must be non-zero. We know that because if both of them were equal to 0, then we could never get that the magnitude of alpha squared plus the magnitude of beta squared is equal to 1. So since at least one of these is non-zero, we can divide by that one. Well, maybe what I'm trying to show right now, I'll just I'll just hold off. I mean, what we can prove a relationship between alpha and beta, their phases. But let's see, maybe we can do that more easily. Just going first with this requirement. Let's see what this will give us. So the magnitude squared of alpha, of course, is equal to this. Let's write this like this. Okay, magnitude squared of alpha plus magnitude squared of beta is equal to 1. Well, the magnitude squared of alpha, of course, is alpha conjugate, and the magnitude squared of beta is beta conjugate, and that must be equal to 1. And now, using our previous work, alpha conjugate will be the magnitude of alpha. Wait, we don't want this either. Let me take a break and see how is the most efficient way to finish this problem. Okay, sorry about that. Obviously, and I'm sure you probably have already figured it out. I was making this much more complicated than it needed to be. So let's get rid of all this. It's not incorrect. It's just not necessary. As we said, when we multiplied the matrix X by alpha beta, we got beta alpha. So over here on the left hand side of the equation we get beta alpha, on the right hand side we get alpha beta. And so whether we compare the first terms or the second terms of those two vectors, both give this conclusion that alpha is equal to beta. And of course, if alpha is equal to beta, then that implies, of course, that the magnitude of alpha is equal to the magnitude of beta. And if you substitute that into this equation, that the magnitude of alpha squared plus the magnitude of beta squared is equal to 1, you get 2. Well, let's just do it one step at a time. So we have magnitude of alpha squared plus, and remember the magnitude of beta is the same as the magnitude of alpha, so we have magnitude of alpha squared again is equal to 1, or 2 times the magnitude of alpha squared is equal to 1, or magnitude of alpha squared is equal to 1/2, or the magnitude of alpha is 1 over square root of 2. And as we already said, magnitude of alpha is equal to magnitude of beta, so we can also say that magnitude of beta is 1 over square root of 2. And now finally, alpha is equal to, as we wrote above, magnitude of alpha e to the I phase of alpha. Beta is magnitude of beta e to the I phase of beta. So alpha is 1 over square root of 2 e to the I phase of alpha. Beta is 1 over square root of 2 e to the I phase of beta. But remember, alpha equals beta, and so that means that the phase of alpha is equal to the phase of beta, and let's just call that theta. So our final conclusion is alpha equals beta equals 1 over square root of 2 e to the I theta. So our state C is represented by the vector 1 over square root of 2 e to the I theta, 1 over square root of 2 e to the I theta. Or to put this in the ket form, this would be 1 over square root of 2 e to the I theta. Well, let's write it perhaps like this. 1 over square root of 2 e to the I theta 0 plus 1 over square root of 2 e to the I theta 1. But of course, a universal phase term is irrelevant And so our final answer is C, is 1 over square root of 2, 0, plus 1 over square root of 2, 1. This is the state that is stabilized by X. So this lecture will terminate there, and we'll have a couple of questions on these two ideas.